Today's lesson is on exponential models. You need to have a calculator today. So if you don't have a calculator right in front of you, stop, go get a calculator so you'll be prepared. Now, if I have $500 and I invested at 10%, I don't multiply 500 times 10%. That only tells me how much I gained. It doesn't tell me how much I have in my account. So I need to multiply by 100% to keep the 500 plus my 10% gain. So our growth factor, what we put in an equation, is 100% plus the rate of growth, or 1 plus the decimal number. So our growth rate is 10%, or 0.10, and our growth factor, what goes into the equation, is 1.1. And we see 1.10 to kind of represent 100 plus 10%, but really I just need 1.1. Now, if we're multiplying and dividing, we're dealing with linear growth. So y equals 2x plus 3, we have 2 times x. We're growing at a rate of 2 every x units. If I had a growth rate of, or I had a growth amount of 120 over 10 months, I'd divide 120 by 10 to tell me I'm growing 12 units each month. For exponential growth, we use powers and roots. So in an equation, I would have y equals 10 times 3 to the x power. If I wanted to find my rate of growth, if I grew 120 units over 10 months, I'd take the 10th root of 120. Now, that would give me my growth factor. So then I would have to subtract the 1 in order to get my growth rate of 10%. So here's a problem. The population of a town is 8,000, and the population is increasing 2.5% per year. Rewrite an exponential growth function to find the monthly growth rate. So our yearly rate is 2.5%. We want to find the monthly growth rate. So if I take the 8,000 times 100% plus the 2.5%, I have 8,000 times 1.025. So for a year, then I should have 8,200 people at the end of the year. So if you did that on your calculator, if you multiplied 8,000 times 1.025, that would give me 8,200. So a mistake is to think I need to divide this 0.025 by 12 to get a monthly growth rate. Remember, if I'm dividing, that's linear growth. I need to use roots to find my exponential growth. So if I took that 0.025 divided by 12, put that into an equation, okay, I could just have the 1.002083 instead of 0.025 divided by 12, and did that for 12 months, it would come out to 8,202.31. That's close to our original amount, but it's not accurate. So to find our monthly growth rate, what we have to do with this problem is write our equation. We have the y equals 8,000, our initial amount, times 1 plus 0.025, which is our annual growth rate, to the t power. T is after t years. So there's our equation. So now we want to find a monthly growth rate. That's 12 months. So we're going to multiply t by 1, or 12 over 12. And using the property of exponents, we know when you take a power to a power, you multiply the exponents. So that 12 over 12 could come from the 1.025 to the 1/12th, which would be the 1 month's growth. And then times t years times 12 times a year. So 1.025 to the 1/12th power is our monthly rate of growth. So 1.025 to the 1/12th power, or the 12th root of 1.025, is 1.000206. And so our monthly growth rate is the 100% plus our rate of growth. That's our growth factor that's in the equation. So our growth rate, we're going to subtract the 1. And so we can say the population is increasing approximately 0.206% per month. Now, 0.206%, is that closer to 20% or closer to 1%? That's closer to 1%. That's less than 1%. So we have to understand what these values mean. All right, so here's a problem for you to try. The population of a town is increasing annually by 1.8%. What is the quarterly rate of increase? Pause the presentation, calculate the value, and let's see if you get it correct. Our quarterly rate of increase is about 0.447%. We got that because the 1 plus the 1.8% is 1.018. And so instead of taking that to the 1/12th power, which we did over here for 12 months, we have a quarterly rate. So we're going to take it to the 1/4th power, which I could do as a fraction, or 1/4 is equivalent to 0.25. So that gives me the 1.004469994. We subtract the 1 and round off to about 3 decimal places. So about 4 or 0.44%. Now, as you recall, the compound interest formula is A equals P times 1 plus R over N to the NT power. Okay, A is the amount in the account. P is the principal, what we're investing. R is our interest rate. N is the number of times we're compounding this in a year. And T is time, or the number of years. So there's our formula, nice and clean without arrows all over the place. So here's a problem. Michaela invests $5,000 in an account that pays 4% annual interest. How much will she have in the account after 3 years if the interest is compounded according to 3 different schedules? First of all, annually, semi-annually, quarterly, and then monthly, which is 4 schedules. Sorry, not 3. All right, so for annually, that's once a year. We're going to put a 1 in for the ends. Our interest rate is 4%, so our R is 0.04, and the initial investment amount, the principal, is $5,000. Now, you need to be able to calculate this correctly on the calculator. We should be able to do this all in one step using parentheses. So try it out and make sure you're getting the right amount. After 3 years, the dollars that we have is $5,624.32. That's $5,624.32. Now, for semi-annually, we still have the $5,000 principal. We still have the 4% interest rate. We still have the 3 years. But now the N, the number of times, would be what? 2. So calculating that out, we get 5,630.81. Now again, make sure you are doing this correctly on a calculator. If you're not, then you need to figure out and get some help on how to do this correctly. So it doesn't do any good to know how to set it up and then come up with the wrong answer. Quarterly would change what? Yes, quarterly would change the N's to 4. And so calculating that out, we get $5,634.13. And then finally, monthly would change our N to what? Yes, there's 12 months in a year. So again, calculate that, make sure you're calculating that correctly. We would have $5,636.36. So now, want you to try this one. If $3,000 is invested in an account that earns 3% annually, find the amount that's in the account after 10 years if it's compounded monthly. Pause the presentation, figure it out. Let's see if you get the right answer. Setting this up correctly. So let's try another one. If $3,000 is invested at 3% annual interest rate, how much would be in the account after 6 years if it's compounded weekly? Pause the presentation, calculate the value, and then you can resume. 3,000 for weekly would be 52 times a year. And then for 6 years, we'd have times 6. So we'd have $3,591.47. How much would you have if you invested it for 40 years and it was compounded monthly? Pause the presentation, calculate the amount, and then continue. Monthly is N for N equals 12, and 40 years, T equals 40. We'd have $9,945.45. Now, let's suppose for a minute that I took $1, invested it at 100% annual rate for 1 year. So I'd have the $1 would be my principal. I'd have 100%, so 1 would be my rate. So that expression, A equals 1 times 1 plus 1 over n times n to the 1, would represent the amount in the account after 1 year for compounding it n times a year. So now let's find the value for compounding it several different times during that yearly period. So if I do it one time, then n is 1, and that's pretty easy. I really don't need a calculator for that. 1 over 1, and then to the 1 power, 1 plus 1 is 2, and 2 to the first is 2. For the rest, we need a calculator. So now, use 10 in both ends and calculate the value. If I compound that 10 times a year, I have 2.59, about $2.60 almost. If I did it 100 times a year, what would that come out to? 100 times a year, I'd have 2.704813829. If I did 1,000 times a year, you can see I have 2.71692 and so forth. Put in 10,000, and what do we get? The 2.7181 and so forth. If I put in 100,000, I get 2.7182 and so forth. As I keep increasing n, I keep getting closer and closer to 2.7182. So as the value of n approaches infinity, I get closer and closer to a certain value. That value, when n is infinity, is called the natural base, and that's the number e. The number e, just like pi, is an irrational number. E is approximately equal to 2.718281828459. But of course, as a rational number, it continues on forever. And so that number e is on your calculator somewhere. Just like you have a pi button, you have an e button. Now, some of you just have e, and some of you would have an e to the x button. If you have e, you can just hit e and get the value of e. And then if you need to take it to an exponent, you need to use the caret. So if you wanted to square e, you would have to say e, use a caret, and then a 2. If you have an e to the x button, after you press that button, it wants an exponent. So if you want e to the first power, when you push the e to the x button, then you'd have to push a 1 and then enter. If you want e squared, you'd push e to the x button and then a 2 and then enter, and so forth. So find the e button on your calculator, because we're going to need that to calculate some amounts. And you have to use the precise value. So we need e, not just some rounded off value close to 2.718. Now I could compound weekly, or I could compound every day, a day compound, or I could go an hour a compound, or I could compound a second, compound, or I could just compound, just compound continuously. Well, compounding continuously would take that number of times in a year and put it to infinity. And that value, 1 plus 1 over infinity to infinity, we just saw is the natural base e. And so we have a formula for continuously compounded interest. We have a nice pert little formula. The formula for interest that's compounded continuously, we're going to replace the 1 plus 1 over n with the e, and so that's a equals p times e to the RT power. Or again, p is the principal. What's r? R is the interest rate. What's t? T is the time. What's e? E is not a variable. E is a number. E is the natural base, 2.71828, and so forth. So here's a problem. We have $12,600 is invested in an account that earns 3.2% annual interest, compounded continuously. How much will be in the account at the end of 12 years? Using our continuously compounded interest formula, 12,600 is the principal. The interest rate, 3.2%, is 0.032. And for 12 years, time is 12. So again, we need to use the E button on the calculator. So calculate that out, and what you should get is $18,498.63. All right, here's one for you. Read the problem, pause the presentation, calculate the value, and see if you get it correct. You invest $12,500 in an account that earns 4.75% annual interest, compounded continuously. How much would you have in the account after 15 years? Pause, calculate, and then resume. What we plug into the formula is 12,500 times e to the 0.0475 times 15. Is your answer 25,488.53? If that's your answer, I'm taking off a point. Because the answer, how much would you have, is $25,488.53. So we have to remember the dollars in our answer. Now, if we have 2 points, we may want to find an exponential model, or the equation that would take us through those 2 points. So Kylie, who just loves being a math nerd, kept a record of how many emails she sent each year since 2009. She realized that the number of emails was growing exponentially. So what is the exponential model that describes the data? Well, we can see in 2015, she had 1,000 emails sent. In 2016, she had 1,400 emails sent. So we have 2 consecutive years. So these can represent 2 points. Now, 2015 is not an X value. We're not saying since the year 0. We said since 2019, or sorry, 2009. So from 2009 to 2015 is 6 years. From 2009 to 2016 is 7 years. So our two data points, 6 years after the starting point, she had 1,000 emails sent. 7 years after the starting point, she had 1,400 emails sent. So there's our two data points. So now our equation, we can see that if I took the consecutive years, I went from 1,000 to 1,400. So if I multiply 1,000 by 100% plus the rate of growth, I'll get the 1,400. So that growth factor, the 1 plus r, equals the 1,400 divided by the 1,000, which is 1.4. So 1.4 is our growth factor. That's what goes in the equation. Our rate of growth is 40%. So the 100% plus the 40% gives us our growth factor of 1.4. So now our exponential model, we want it in the form of y equals the initial value times the growth factor to the x power. Well, we have to find that a value, that initial value that started in 2009. So we just saw that the growth factor is 1.4, and the y value would be 1,400 after 7 years. So our exponent is 7. Now, to keep things simple, instead of using big numbers, I'll use the number 14. So that's our value in hundredths. So now to solve for a, I just divide both sides by 1.4 to the 7th power. And so if we did that on a calculator, 14 divided by 1.4 to the 7th, we get approximately 1.33. So our initial value is 1.33. So our equation to tell us the number of emails we have after X years would be y equals 1.33 times 1.4 to the X power. That's the number of emails in hundreds that Kylie sends X years after 2009. If I use the 1,400 instead of 14, then I'd have 133 in my initial amount. That would be the initial emails that were sent. We're using smaller numbers, knowing that our answer is in hundreds to keep things simple. So here's a problem for you to figure out. A surveyor determined that the value of the area of land over several years since 2010. The land was worth $31,000 in 2014 and $35,000 in 2015. Find an exponential model for the value of the land. Pause the presentation, find the model, and then resume to see if you're correct. Our model, if we used numbers that were actual numbers, we'd have y equals 19,080.88 times 1.129 to the x. If we want to keep it simpler and had our answer represent thousands, then we could be y equals 19.08 times 1.129 to the x, where whatever value we get is in thousands. Now, sometimes we have data, and so we can use something called regression to find a model for our equations. So here's a problem with some data. Randy is making soup. The soup reaches the boiling point and then begins to cool. Randy wants to serve the soup when it is 10 to 15 degrees above the room temperature of 68 degrees Fahrenheit. How long should Randy let the soup cool? So we have some data. We see that initially it was at boiling point 212 degrees. 2 minutes later, it was at 185 degrees. 3.5 minutes later, it was at 170 degrees. So we don't have any consecutive values, but we do have some data. Now, if we graph those points, we would see that it's not a linear type of graph that we get. The best fit would give us an exponential regression. It's cooling at an exponential rate. And it's not going to get to 0 degrees. It's not going to freeze. It's going to get to room temperature. It's not going to get cooler than that. So 68 degrees becomes an asymptote for that graph. It gets closer and closer and closer to approaching 68 degrees, but it will never cross that point. So when we use linear regression tools, they often need to regress towards 0. We can't have it regress towards 68. So we need to rethink our data that 68 is kind of our 0 point that we're getting to. So if we take each temperature and subtract 68 degrees, we get our degrees above room temperature, our target temperature. So now we need a linear or an exponential regression function. If you have a graphing calculator, you might have that in your graphing calculator. Okay, and then you could put in a list. We'd put in list 2, which is our values above 68 degrees. And of course, list 1 is our times. Now, 3 minutes and 30 seconds, we're not putting 3.3. 30 seconds is half of a minute, so that's 3.5. 7 minutes and 30 seconds is 7.5 minutes. So those are our X values that are putting in, and then the Y values we're putting in for our target above 68 degrees. So if you Google exponential regression, probably the first one that comes up is this website. So you want to go to that website, okay, so that we can enter in some values and try this. So you may have to go back and forth between the presentation in order to try this out. So go to this website or Google exponential regression calculator and get to that point. Now this one is pretty simple. So when we get there, we see a table and it has a place to put X and Y values. The table may have some values in it already. So if it has values in it, you need to hit clear in order to clear those values. And then we're going to put in our data. So we said at time 0, that's our first X value. We had 2 minutes, that's our second X value. So we can just hit 0, enter, 2, enter, 3.5, enter, and fill in the X values. We wanted the Y values that represent the temperature above 68 degrees. So we're putting in the 144, 117, and so forth. So put those values in the table, and then you can resume when you have that table filled in. Once you have the table filled in, then you want to hit the execute button. So hit execute, and then you get on the page a table that shows you some functions, and you get a rough graph, but you can see the graph is approaching 0. That's really our 68. What's important is the A and B values. Remember, our exponential function is y equals a times b to the x value. So there's our A and B functions. So we can write the equation. There's our A value, 126.35. There's our B value, approximately 0.9492 to the x power. That would get us to 0, but we said we want to get to 68. So we have to add 68 to this function. And that would push all the values up to get the correct values. So that's how we can use an exponential regression calculator. Now, according to this model, what is the approximate temperature 35 minutes after cooling started? Calculate that and then resume the presentation. X is the number of minutes, so we'd be putting in 35 for X. So putting in a 35 for X, we'd get 88 degrees. When will the room temperature reach 80 degrees? Pause the presentation and see if you can figure that out somehow. Okay, how did you figure out when the temperature will reach 80 degrees? Well, 80 degrees would be the Y value. So one way would be to do some trial and error until you get the closest that you can to 80 degrees. If you had a graphing calculator, you could put this equation, y equals 126.35 times 9.9492 to the x plus 68, into the graphing calculator in the y equals function. And then you could choose the table button and you'd have a table of values. And you could see that we reach 80 degrees when x is approximately 45. So it'd be about 45 minutes, okay, when that reached 80 degrees. All right, this concludes our lesson today. Good luck doing the work.